Now, I know how much fun you had with Gauss's law. We're going to introduce a very similar law, only not now for magnetic fields. A very important law. It's called Ampere's law. What Ampere law says in general, I'll say it again on the next slide, is the circular integral of V dotted with dl is going to be equal to the current that's enclosed multiplied by mu naught. Now, very often we choose our circular path. That's what this guy right here means. We choose that to be something that makes sense. Consider, for example, a wire that's coming out of the page. The current's coming out at us here. If we chose our circular path to be in the same direction as B, kind of in the region I'm highlighting right there, then this simply turns into B multiplied by 2 pi r. How much current enclosed? Well, that's just going to be equal to I multiplied by mu naught, and I'm going to get the familiar B is equal to mu naught to I divided by 2 pi r. Saved a lot of calculus right here. If we choose our path in the opposite direction of dl, then B dotted with dl would be negative, and then I would have a negative mu naught times I enclosed, kind of shown right here. And lastly, if we chose a path that didn't enclose any current, taking a look at this path right here, the path kind of goes like that, like that, like that, like that, then the enclosed current is going to be equal to 0, and you could convince yourself that there's going to be no contribution here, no contribution here. Here B and dl are in the same direction, here they're in opposite directions, but the magnetic field is going to die off like 1 over r, and we could go ahead and calculate all this out, but at the end of the day, circular path that doesn't enclose any current, integral of B dotted with dl is equal to 0. Now, I showed you the circular case on the last slide, but it is true for any given path that you choose. The integral of B dotted with dl must be equal to the current enclosed over multiplied by mu naught. And really it follows the same argument as Gauss's law, is that I could take any path right here and I could break it into components that had perpendicular and parallel components, and they would all add up such that at the end of the day, even though this integral would be pretty nasty, I would still be able to boil it down to just current enclosed mu naught. Now, if I had more than one conductor, more than one wire going through it, choose my path kind of like that, and I could say, well, what is my current enclosed? Take a top view of this perspective view right here. You can see that this guy is going to go through these 3 currents. Let's take a look at what the magnetic field is. Do the right hand rule for I1, it's going to be in that direction. Do the right hand rule for I3, it's going to be in that direction. You do the right hand rule for I2, the current is going to be in that direction. And so in this case, the integral of B dotted with dl is going to be equal to I1 plus I3 minus I2. Why? Because right here I2 is in the opposite direction as my path. Now, just one caveat here is we're kind of assuming that the current is going to be constant and that there are no magnetic materials or time-varying electric fields that are present. In that case, this would not be true. However, we'll generalize this when we talk about chapter 29. So what we can then do is say, hey, well, what's the magnetic field going to be inside of a very long conductor? Well, we have some current flowing through some wire, so let's define a current density, which is going to be the current divided by the surface area of the entire wire, so pi big R squared. Now let's do Ampere's law, integral of magnetic field dotted with dl. Let's take my path to be inside of the conductor, following the direction of the magnetic field, so R is less than big R here. That's going to be equal to current enclosed multiplied by mu naught, and that's going to be J multiplied by pi little r squared, or current pi r squared divided by pi big R squared. My circular integral is going to say b multiplied by 2 pi little r is equal to all that stuff. Cancel those guys out. And I'm going to have I cancel out one of those r's right here, multiplied by r, divided by 2 pi big R. So it's going to be a linear relationship inside. And then outside I'm going to find what I derived 2 slides ago, which is just mu naught I over 2 pi r. We can also use Ampere's law to find the magnetic field inside of a solenoid. Also could call this an electromagnet. And essentially what that is just going to be a bunch of wires that are shaped in the shape of a cylinder. You can do the right hand rule, got the current flowing in that direction. You can convince yourself that you're going to have some magnetic field going through this solenoid in that direction right there. Here the current's been reversed, and you can see even with just a couple of coils right here, the magnetic field is actually quite uniform inside of this solenoid right here. Well, let's figure out what the magnetic field is going to be inside of this solenoid. What we can do is we can take a circular path, or not a circular path, but an integration path in this direction kind of right here. And one thing to kind of keep in mind is this little break right here that says that BC and DA are very, very, very long, such that the magnetic field is going to be 0 outside of CD, or in this path length CD. So what that means is that the integral along our path, b dotted with dl, that's going to be equal to 0 along, let's just say, BC. It's going to be 0 along CD. It's going to be 0 along DA. Why is it 0 along CB or BC and DA? Well, if you look at it, the magnetic field inside of the solenoid is pointing in that direction right there from the right hand rule, which is perpendicular to BC and DA. So integral of b dotted with something that's perpendicular with it, it's going to be 0. And so what we're left with is the magnetic field multiplied by the length of the solenoid. That guy is going to be equal to mu naught multiplied by I enclosed. Well, how much current is enclosed? Well, I enclosed is going to be equal to the number of coils, 1, 2, 3, 4, 5, 6, 7, 8, multiplied by the current carried in each coil. It is also sometimes convenient to say, you know what, I want to not define this for some given length. I want to define this for some unit length. I want to say I have some number of turns per unit length of my solenoid coil. So that's going to be a little n, where little n is just the total number of coils along the length. And what that allows me to do is that allows me to write my magnetic field. It's going to be equal to mu naught number of coils multiplied by I, where I've essentially divided that side by length, divided that side by length, and then substitute that n in. So here I have my magnetic field. We can also have a solenoid that's shaped like a toroid, could also be less technical, let's say a donut-shaped solenoid, if you will, where we have some current coming onto this toroid, kind of wrapping around it, kind of like that. You can go ahead and do Ampere's law and say, well, let's take a look at what the magnetic field inside of this solenoid is going to be. Wow, look at that. I have no charge enclosed, so I'm going to have 0 magnetic field inside of it. If I chose to do my path out here, then for every one of these guys coming out, I'm going to have a similar guy going in. So my magnetic field is going to be equal to 0 outside of it. Do the right hand rule and you can see that the magnetic field at any given point is going to be along this shaped path right there, and all of the magnetic field is going to be inside of this guy. Really, this is actually quite useful if you're trying to trap charged particles. The last thing we'll talk about is why are some materials magnetic and others are not. That leads us to this concept of the Bohr magnetron, which is essentially saying if we have an atom, it's got some positive charge on the inside, and it's got these electrons that are whipping around it right here, that looks like a current loop. So the Bohr magnetron is essentially an atomic current loop. And what that's essentially doing is saying, hey, this guy is behaving like a magnet. There's going to be a magnetic moment. So atoms are going to behave like they are magnets. So we're showing kind of the magnetic moment right here. We also have the angular momentum vector. Don't have a whole lot to say about that. But really, if you introduce a magnetic field into an atom, so I get some magnetic field going in there, the atom's going to behave differently depending on what the material is. Essentially, this magnetic moment is either going to line up with that field, it's going to have a force of attraction, in which case we say that this item is going to be paramagnetic, or it can essentially repel that magnetic field, in which case we would say that it's diamagnetic. This leads us to a concept that you're probably more familiar with, which is ferromagnetism, which essentially says that if you expose a substance to a magnetic field, it may retain some magnetic properties. What we need to do is we need to take those Bohr magnetrons, those moments that I was talking about, and say we're going to have these magnetic domains inside of a material where essentially we kind of lump together a whole bunch of different magnetrons that are all pointing in the same direction. Say, in general, in this domain right here is pointing in that direction. In general, in this domain right here, they're all pointing in this direction, and so on and so forth. Now, if we were to expose this guy to a magnetic field, then what's going to happen is these guys are going to shrink down, and you can kind of see that now this domain is a little bit larger, this domain is a little bit larger, so there's more pointing in this direction right here. So this would essentially mean that we have a weak magnet. Expose it to a stronger field, it's going to shrink down even more, and we're going to have a much stronger magnet at the end of the day. So here we're going to have a strong magnet. Now, in reality, how we create magnetic materials is that we would take an object, we would heat it up, that makes the domains shift around a lot easier. We then use a solenoid to create a magnetic field. We can then cool down the material, take away the magnetic field, and at the end of the day we're left with a magnet. This leads us to the idea of hysteresis, which is essentially also kind of a memory of a magnet. The way that we would create a magnet is we'd apply a magnetic field, or we'd apply some current to it. So we can kind of think of this axis right here as being current, and then this M is going to represent how much we've magnetized our piece of ferromagnetic material. So we would maybe start off right here with some with essentially no magnetization, apply some magnetic field. We would then decrease our current to 0, and we would say, well, look, I still have some magnetization left, so here I still have a good magnet. From that point, it takes a fairly large magnetic field in the opposite direction to bring that magnetization back down to 0. Then I could kind of work my way downwards and start coming back towards the 0 point with my current, and here I have a very good magnet that's now pointing in the opposite direction, and then the same is true. Now, if I didn't heat my material up, then my hysteresis curve might look kind of like this. It would be very shallow, where I go up like this and I come back down, and I'm left with a magnet that's maybe not so strong. So this is the type of curve that you want to see if you're trying to generate a good permanent magnet.